Hello students, welcome back to Embedded Pathashala. This is lecture 5 in Linux system programming course. So in the previous lectures, I have shown you what is Linux architecture and what are compilation stages available, how to stop compiler at each stage, how to read the assembly file, preprocessor file, machine file, and these things, right? So now I hope you are comfortable with Linux environment and the terminology. So let's dive into system programming concepts. So before diving into system programming concepts, let's understand few basic things. First, what is a system call? So in the previous lecture, I have shown you there are two spaces. One is user space and the kernel space. User space is the low privileged mode and kernel space is the high privileged mode, which can directly access hardware and memory in the physical memory, right? So now for user space applications to interact with kernel space, they need some kind of mechanism, right? So that mechanism is called as system call. So what system call does is it is basically an interface through which the user applications can enter into kernel mode and access the system resources because user mode cannot directly access system resources. That is the reason to switch from user mode to kernel mode, we need some interface and it is called as system call. Now, once system call is used, the system will run in kernel mode. So from user space mode to it switches to kernel mode. So how we can call this system call is we can directly try by calling the system call. So we can directly give the API of the system call and it will function. So in user space application, we can directly write some system call and access its functionalities. We will see how we will write system calls in upcoming lectures. Next, what are the some examples of system call that are available in system programming? So few system calls are open, close, read, write. So in the very first lecture, what I have told you, I said in Linux, everything is a file, if not a process. Only two things, right? So to perform any operation on file, we need to first we need to open the file, right? So to open that file, we will use open system call. After opening the file, we need to do operations like read and write, right? For that purpose, we will be using read system call and write system call. Once this is done, we will close the file by calling the close system call. So basically, this is what system calls are. So now one more example I want to give you. Basically, the printf what we use is basically a glibc API, right? The standard library. What will happen, this will in turn again call the write system call because printf you can understand, but in internally it should be translated in some way so it can go to the kernel and somehow print the operations, right? So for that purpose, the printf will be actually converted into write system call and that write system call will print the data. So how this printing and translations, these things will be happening, I will show you in detail in upcoming lectures. For now, um, you understand few things. In Linux system programming terminology, whenever you hear a standard input, that means keyboard. Standard output is terminal. Standard error is some, by default, some standard error. These are assigned with some values like 0, 1, and 2, and these are called as file descriptors, which are available by default. So if what I said you in the earlier lecture, right? We will be having some file descriptors to access the files. So every file descriptor is some small positive integer value, and these three integer values are directly assigned. So this is how a system call basically works. Next we will see. Yeah. So this is some important concept I will try to put in a simple way. So you write a system call, but kernel should understand how this what system call is passed and what are the parameters that are passed, and it should execute. For example, if you send open system call, it should not perform read system call or write system call. It should only perform open system call and return, right? So how kernel will understand is, so in user code, you will write system call. Then there will be some wrapper function in glibc for write. and the arguments that are passed in this wrapper function. So this wrapper function, what it will do, it will raise an interrupt to the hardware. And after this interrupt, the application switches from user mode to the kernel mode. So before switching to kernel mode, what it will do, every system call will have some number, which we call as system call number. It is written onto some specific CPU register. Which register we will see later. For now, you understand it will be written into some CPU register. Then after switching into kernel mode, it will enter into interrupt handler mode because we have triggered interrupt stating some system call has been triggered, right? So now what will happen? This interrupt handler will check for system call number that has raised the interrupt. So all these system call numbers will be stored in system call table. So internally we will maintain one table which is called as system call table where all the interrupt number system call IDs will be mapped. So when an interrupt is raised, we will check what system call raised this interrupt and accordingly we will execute that particular system call. Here write right. So write system call will internally trigger again sys write and this the arguments what you have sent will be written and the system call will be executed and after the successful execution it will enter into it will return the wrapper function and finally it will go to the user space code. So this is how basically one Linux system call tracing will happen from user space to kernel space and go back. So let me explain through some small example. So basically user mode will write some code which will call write system call. Here, a glibc write wrapper will be there because directly we cannot access kernel, so some wrapper functions will be given. So this will internally call this wrapper function and this wrapper function will raise an interrupt. Okay, so when this interrupt comes, user mode switches to the kernel mode. And in kernel mode, we will have one system called table. So this system called table will check what interrupt has been raised. For example, assume write means 1 if we think some number. Then okay, this number means I should trigger syswrite internally. So it will call original syswrite API which will write the data to the screen which means standard output, right? Once it is done, it will return to trap handler and it will exit the kernel mode. So after this, it will go back to user mode again. This is the reason we will see. This is how actually once you call the write API, the output is written onto the screen. So in interview, if interviewer asks, can you explain how the system call works actually, you need to explain all these things with an example. Okay. So now this can be your interview question. So if anyone asks, is printf a system call? Then you should tell no. System call, printf is not a system call, right? Then what is system call? Printf internally calls write and it goes to syswrite, right? So that is the original system call. Next, this is also one interview question. Where does system calls execute? They execute in the user space, not sorry. They execute in the kernel space. They are called in the user space. Where does library functions execute? Library functions means your printf. They execute in the user space. These are some knowledge check you need to know. Next. So till now you are comfortable with concept of system calls, right? Now let's start with the programming. Now remember one thing. In Linux, everything is a process or a file. That's it. So when you are creating a file, what is a file then? So basically, file is a memory location that can store some information. That's it, right? That is the purpose of file. So when you create a file, we need to give some permissions to that file. Whether you want to that file to execute in read-only mode or write or execute or both read, write and execute. These are some permissions we generally give to any file, right? So in Linux, to give these permissions, we have some numerical methods. Like we will denote read operations through 4, write 2 and execute 1. If I give, okay, I will explain in detail. For now, you understand the 3 permission and each permission has some value. Okay. And also in Linux, there are different users like user, group, and others. So every user will have different permission. Everyone should not have every permission, right? To handle such things, we will be using this users concept, user, group, and others. So how we will assign this permission and these things I will show you. Yeah. Now, also remember one thing. In Linux, as I said, everything is a file. Then there are different files in Linux system. So there are regular files. If you see something starting with hyphen, it is a regular file. If something starts with D, it is a directory. If something starts with C, it is a character device file. Something starting with B, it is a block device file. S means socket file. P is named pipe and L is for symbolic link. So we will see these things also in terminal in coding exercises. Okay, so I hope now you are clear with these things. So let me present my terminal to you. Yeah, so for now, first let me show you how this glibc APIs will work. So what I will do, vi from hello.c f hello world. So if you see in this example, I am not using any system calls. This is a standard printer which is a glibc API and it is available through standard library in stdio.h. So I hope you are clear with this part, right? So here we will do, see, we saw right how to compile and these things in previous lectures. So using same thing. Yeah. So now you have seen how this is printed onto our terminal because by default any process standard output is terminal with process ID 1. So this is the reason you are seeing the print on the screen. Now I will show one more program. So here without using printf we will try to print the output onto the screen. So here hash include std.h. Here we are not using any stdio.h because we don't want any standard library. Okay, so void main void main size underscore t some length. In 10, I will give some message length of 0. Let it be. And some, I want to create some buffer of 100 bytes. Done. Now what I will do, strcpy buff. This is write call on screen. And the length of how much we want to print, right? So I'll print some 20, some random number, but we can do it later if you want. Now it's length equal to write. One means standard output. That means screen. Onto screen, I am writing contents of buff, which we copied earlier here. Then I am giving how much data to copy. That is message length. Done. Exit. So what I am doing, basically I'm copying some string into buffer. Okay. After that one, I am writing data from buffer onto the standard output without using any library function. That is the concept. Now we will see what happens exactly. ECC FNO PG3. Yeah. Now our executable has been generated PG3. Okay. Now dot slash Some wrong. Okay. So here, yeah, you understood the concept. I am not exactly printing the message length, so that went wrong actually. So let me cover that one. Message length equal to str length of. I hope now things should be clear. Yeah, sorry. So that's some kind of logic issue, sorry. So yeah, now if you see, without writing any printf function also, I am able to print some data onto the screen using the standard, the system calls, right system call. So this is the concept of system calls. Printf is basically some user defined like standard library API, which in turn calls the write system call. So directly by using write system call also, we can print the data. Some random data I have printed. Don't worry about this one. But this is the concept of how to use a write system call. So now I hope you are clear with how the system call works, right? So now let's deep dive into more system call examples. Before that, we have discussed few things, right? How what are different files available and the permissions, how to set different permissions. Now I'll show you one example. So if I type here ls-lrt, you can see few things, right? Here, the first one, D means directory, hyphen means general file. Okay, I'll show more examples. So here things are divided into first block is user, next block is group, and next block is others. So for user, I have given permissions like read, write, and execute. All permissions are given. For group, we have given all permissions. For others, we have only given read and execute, but not write. Similarly, if you see one executable hello, user has read, write, execute, group has read, write, execute, others only have read and execute. Now I want to change this permission for everyone to read, write, and execute. So what I will do, chmod 777. That means 7 means what? 4 plus 2 plus 1. Read, write, and execute. For user, read, write, execute. For group, read, write, execute. For others, read, write, execute. And I'm giving the file name hello. Done. Now if we see, hello has read, write, execute, and read, write, execute. Everyone got every permission. So this is how permissions are basically changed in the files. So if you feel this some person should not get any permission, you can remove. We will see that also. Chmod 444 hello. This means now hello has only read permission. If you see the difference in green color, previously it is executable file because read, write, and execute. Now if you see it's general file, read only read permission. So we have removed the executable permission. So similarly, you can change different permissions to the files based on your requirement. So after this lecture, please practice different file operations by giving some different values and check the output. Okay, so this is how these things will work. Now, if you see, I will go to one directory and here you can see different files available, right? In the Linux file architecture, I have mentioned you the importance of device files, right? I mean this directory. So here you can see C means character drivers, D and C means character drivers, B means block drivers, and similarly we have multiple things. L means some system links. So this is how basically see, because in Linux everything is a file, but that doesn't mean every file is unique, right? Every file has its own importance and other things. So all these kind of files are grouped based on their uh, properties. Character files are denoted by C, block files by B, and their directories by D, like this. Symbolic links by L. This is how we will be doing. So we will describe more about these things. See, you can observe from here. Initially, I told you, right, standard input, standard output, and standard errors. Those are the symbolic links of std out, in, and error. So whenever std out you will be using, here what we are doing, the file descriptor 1 is assigned. Std in, file descriptor 0, std error, and file descriptor 2. This is how file descriptors are assigned. And also how file descriptors are assigned, that will be defined in this directory. Basically, every process will have their unique file descriptors, and all those things will be handled in the proc directory, which means process directory. So we will explore more about these things in upcoming lectures. For now, if anyone asks you, you should tell this is how the standard input, output, or error or file descriptors will work. So this is the concept behind the standard input, output, and standard error. Okay, so now let's get back to coding. Now what I will do, open system call. Mhm. Yeah, so now what we have discussed, everything is a file, and we saw how the file descriptors are assigned and how the file descriptors 0, 1, 2 will be actually working, right? So after that, we will see how basically IO operations are performed on the files. So IO operations means input output operations on files. So in this topic, we will discuss like what are the different system calls available to perform this IO operations. So there are few keywords that you need to know. One is file descriptor, other is open system call, read system call, write system call, close, and lseek. So what are these things? We will see. File descriptor. So any system call, I mean, to perform any operation on a file for any system call, you need to able to access that file. That means there should be some way or mechanism to access that file, which is called as file descriptor. Means once you successfully opened any file, the value that open system call will return is called a file descriptor. And it is some positive small integer value that basically stores the open system access to the file. So using this file descriptor, you can able to access the file and do all the IO operations on the file. So how this file descriptors will be there, we will see. So this one, I have kept POSIX names like some wrong info. Sorry for that one. Basically, file descriptor 0 means standard input, 1 means standard output, and 2 means standard error. So that all we have seen in the previous lecture in device how they will be handled, right? So one more tip, in Linux, everything is a file. Even the keyboard, what you connected, the mouse, everything is file. Remember this one. That's the reason we will have this file operations. Yeah. Now open system call. So open system call, what it does. So this is the first system call that you need to perform to open any file. Only if you are able to open the file, you will be able to read the file or write into file and close the file. So open system call is the first system call that needs to be executed. So, okay, let me show you in detail. Yeah. So, okay. To similarly for printf, how you will be using stand stdio.h header file. Similarly for open system call also, we have few header files that need to be included. This how we will get this information, I will show you on screen. Next, to open any system call for printf, how you will pass arguments. Similarly for opening system call also, we need to pass few parameters. For example, to open any system call, you should send like first path of the file. Where is that file located? What file you want to open? That information contains in this parameter. Next, flags. How you want to open file in this path? Whether you want the file to be open in read only mode, only for reading purpose, or write only mode, only in writing purpose, or for both read and write. We should tell this kind of information, right? So that kind of information will be passed in the flags parameter. Next, mode. See, as I have shown you in the previous example, how we can change the mode, right? Read, write, execute, or only read, write. These kind of things should be set in beforehand. So when we are creating any file, that permissions will be helpful. So that arguments we pass in mode parameter. How we will do this, I will show you while coding examples. Yeah. So these are some parameters that we will be passing in open system call. One is write only or write only. That means I want to open the file only in write only mode. So for writing operations, we will use this one. Also, if I want both read and write operations to be performed, then I will use the read write flag. That means I can do both read and write operations. No, if I want to open the file only for read-only purpose, so I will be writing as read-only purpose. Also, we have one more flag which means create. That means you are trying to open the file, but that file is not there. So we will tell the compiler to create the file and do the required operations. So to do that kind of operations, we will use O underscore create. Okay. So this I will show you an example. Yeah. Next. So now you know what is open system call, what parameters we pass in open system call, right? So now one more thing you need to know, when open system call is success, it will send one small integer value which will be used as file descriptor for later operations. In case if open system call fails, then we will send some error and we will print that error. Whether the commonly used errors in open system call are, one is e-access. That means there is no access to open this file. Next, e-exist. That means that particular file you are trying to open does not exist. That is one more error. And E is directory. That means whether this file, I mean this directory exists or not, we need to check. So that is one more error that we will be getting. So these are the errors that open system call can return. And also I discussed if open success, it returns file descriptor. This is interview question you need to remember. If open call success, it returns file descriptor. If it fails, it returns the error value. So we will see in detail about these descriptions. One second, I'll share my. Yeah. So to get information about any system call, what you need to do is, for example, we have studied about man system call, right? Sorry, open system call. Linux provide one tool which is called as man pages. So man pages will contain every information about the system calls what you are using. So you can simply type man to and open. So see, this is the complete documentation related to open system call. So this is the reason why I added these header files for open system call. And this is the path name, flags, and mode that we are discussing about. So always remember, if you get any doubt about system calls, you can simply refer the man pages and you will get the required information. So what this system call does, and different parameters that need to be passed, return values, e-access, e-busy, these things what we discussed. So everything we will get information from here. So if you want in-depth knowledge about any system call, you need to refer this man pages. So this is one useful information for system programming. Done. Now we will start coding examples. So yes, I was feeling a bit cold actually, so don't mind. Now let's create one directory, mkdir day coding, right? MD1 vi open. What we can do, vi pg1 open.c. Now we will start writing. So we have seen what header files need to be included, right? So let me include them. Sorry. So this is some file descriptor. File descriptor means small positive integer value, right? That is the reason I have created as int. Now fd equal to open. So what we will do, we will try to open some file that does not exist. Okay, demo.file. Now flags. How I want to open this file? I want to open it as read-only file. Done. Read-only file. Here we will write one error check. If file descriptor equal to -1, that means open system call failed, right? So we will tell open, sorry, /n and open system call failed. And I want to see why it failed. Then what I will do, I will print the error. This will show why system call failed. In case if system call is success, printf file open successfully. That means our open system call is successful. Done. This is small program to demonstrate open system call. Now I will compile that program. -o pg1 underscore open dot and pg1 underscore open dot c as pg1 underscore open. Yeah. Now if you see, we will get error open system call failed because there is no such file or directory. So what is the file we are trying to use in this program? Demo underscore file. Now I'll do one thing. Vi demo underscore file. I will create some demo dummy data, save it, done. Now we will run this file again. Now you see file opened successfully because it is able to find this particular file demo underscore file. Hope you understood the logic. So this is how open system call basically works. Done. Now let's see one more example. So here what we will do, vi pg2 underscore open dot c. C I hash include hash include TL. So for today, your exercise is what are these header files and why we include these header files that you need to study and post in the comments. Okay. Hash include error number.h. Done. Now int main, what I will do, I will create some file descriptor and I will try to open the file which is create. Then, so this file also it is not there. So we will see what will happen. So create. Then I will try to open in ORTWR in read write mode. In case if it fails, I will tell O underscore create. Also, permissions I will give is 0774. That means user will have read write execute, group will have read write execute, others will only have 4. So we will see what will happen if file descriptor equal to -1. That means it returned error value. Printf error in opening file, and the error value is error. Else printf file open success, right? Now escape and WQ. Now I'll show you. See, there is no file called create, right? Now we will try to execute the program. Scope open and pg2 underscore open dot c. That now dot slash pg2. Here, wait, I think some logic error I have missed. Okay, it's because the file is not there, so we created the file and we have completed the execution. That's the reason we are able to print file open success. So what exactly happened here is the default expectation is we should get error like we are not able to open the file like discussed earlier. But this did not come because of the write system call. So here I am trying to open this one in this way, but actually this O create dominated and it created a file with permissions this one, and then we are able to open the system call successfully. Yeah, if you see here, we have created a new file like create demo. So, and create demo permission 7, 7, and 4. This is what we have given, right? So basically, this is how open system call will work. Yes, friends, sorry for that one. Yeah. So this is how a system, right? Open system call will work. Now we will show one more example about open system call. So let me do one thing here. Let me simplify the things. So just what I will do, cp pg2 underscore open dot c to pg3 underscore open dot c. Okay. Now pg3 open dot c. Yeah. Here I want to show you one thing. So instead of giving like numerical 774, you can also try one more way of giving file permissions, which is, so it is, will tell as I, this is a standard denotation, then read, write and execute for user, and again as I read, write, execute for group, then as only read for others. Okay, now we will see what will happen. Okay, already create demo is there, right? So what I will do, create demo one. So ccm -o pg3 open, then pg3 open dot c. Now see pg3 open file open success. Now ls-lft. See, create demo one is the file that we created, and the permissions we have given is read, write, execute for user, read, write, execute for group, and only read for others. So this is how we can open file and create file using different flag parameters. So these things you need to know before starting Linux system programming. So going in depth into system programming. So now I hope you are clear with open system call. Okay. Now I'll show you one more example. Yeah. So now see, for example, we have seen how to open a file, read write mode, and create the file if it does not exist, right? So there may be scenarios where you are trying to create a file which is already there. So in that case, we need to exclude the duplicate creation. So we will see how we can handle that scenarios. Do pg4 open exclude dot c. So here, what I will do, stdio hash include cntl.h include member.h and void name and some file descriptor value if it is trying to open the file, which is, for example, x file. I will create one file, and here I want to open the file in read write mode. If it does not exist, I want to create the file, and again I am trying to create the file, then I want to exclude the file. Then I will give permissions 0774 and exit. So if file descriptor equal to -1, then printf open failed, and error I want to print like done. Else printf open is success when file descriptor equal to what file descriptor exactly used we will see. Done. Now gcc pg4 hyphen pg4 exclude. So open system call success and it printed file descriptor equal to 3. Why? Because 0 for standard input, 1 for standard output, and 2 for standard error. Next available integer value is 3. So that is the reason 3 is the file descriptor that has been assigned for this particular file. See, if I run the program again, now we are trying to fail because initial stage that particular file is not there and ocreate has created the file. When you are trying to run again, file is already open, so you cannot create again, and you because of that o exclude flag we are getting this error stating file already exists. So this is the concept about open system call. So here you have seen what is open system call: parameters to be passed, flags to be passed, and if file does not exist, how to create the file, and if file already exists and trying to create, how to exclude the file. So this is the terminology about open system calls. Now we will see read system call. Okay, wait. Yeah. So read system call. Basically, once you open the file, you should be able to read data from the file, right? So to perform such operations, we will be using read system call. And read system call will have its own man page and it will tell all the necessary information like header file, syntax, everything. So if you see syntax of read system call, we will be having one file descriptor and some buffer and count value. File descriptor will tell which file has been opened. Buffer will where input data need to be placed, and count how much data you want to read. So this information will be given in the read system call. So once read system call is success, it will return number of bytes that are read. If it fails, then it will return the error. So this is the concept of read system call. Now let's see in terminal how this can be done. Yeah, as this is completely freshers course and beginner level course, I'm trying to keep the concept and examples that we are going to use very simple. So in the next course, the advanced Linux system programming course that we will be launching. So in that you will see high-end logics and everything. So this course will get you hands-on about Linux system programming. So don't think that we are teaching you basic things. So keeping freshers in mind, we are doing this kind of curriculum. Okay. So now let's start read system call. Hash input stdio.h, and the header file we saw hash include stdlib.h, hash include std.h, cntl.h. So I said you right, your task is to understand what are these header files about. So void main. Then I'll create one file descriptor. And this one you will understand why I'm creating. So I need some buffer. Char of 20 bytes is enough. For example, let me assign it to 0. Done. Now fd equal to open some read.txt file. I want to open it in read only mode. That's it. Done. And exit. Now what I will do, I will call read system call. What we studied earlier, read will return number of bytes it has read, right? To store that value, I am using one size variable. Okay, here I will do read file descriptor. Read from where? From the opened file, which is denoted by file descriptor. And where should I store that data? I should store that data in some buffer. Then how many count, right? So how many bytes you want to read? I'll just give us 10. Done. Sorry, students. Now what I will do, so we will terminate, right, generally in strings. So same thing I am doing. Now what I will do, printf, the read bytes are, what are the bytes we have read? Percentage. So buff will print the bytes that we have read. So, wait, here things went bad. This one, then exit. White failed. Then next operations we are performing. So we will see how things will work. Remember, read.txt is the file we are trying to create. gcc -o pg5 read and pg5 read.c. Now /pg5 read error because there is no such file or directory in our working space. So vi read.txt I hello, this is demo for read sys call. I will exit. Now I will run it again. See, I said to read 10 bytes. So from the open file, it is reading 10 bytes. 1, 2, 3, 4, 5, this space 6, 7, 8, 9, and 10. And finally, we are terminating with null character, right? So this is how the read system call will work. Hope you are clear with read system call. So till now you have seen what is open system call, what is parameters that we pass, how to create, how to exclude, and about read system call, right? So now next tomorrow we will be seeing about write system call and the different operations that are available. Yeah. That's it, friends, for today. So I have shown you like what is system call, different types of system calls available, open system call and read system call, right? So tomorrow we will see about a write system call. So this is the concept about system call, friends. Tomorrow we will meet again. If you have any queries, please post in the comment section. Thank you.